Hello, chemistry students. This is Dr. Kirschner. This is lecture 1 from Unit 8. This was done for the B and D blocks on January 21st and for the F block on January 22nd, if you're keeping track of dates. Okay, so we're starting Unit 8. Your PowerPoint notes are in the class notes folder of OneNote, and your homeworks are in the homework folder of OneNote. This is the lecture for homework 1 of Unit 8 concerning basically writing out chemical equations from statements that describe a chemical reaction and also balancing them. So that's our main focus, and you'll see that in the homework. All right, let's get started. A couple of preliminary things on chemical reactions. Okay, chemical reactions is a process in which one or more substances, chemicals, are changed because they react together into new substances. What really happens then is you either break bonds, make bonds, or you do both. So you have to change the connections between atoms. When you do that, you make new chemicals with new formulas, which have new physical and chemical properties. Certain chemicals react with certain chemicals. It's not like all chemicals can react with anybody they want. They're very specific. Some chemical reactions happen very quick. Some you need to put a lot of energy in, and some are just very slow. But they're very specific as to which substances they'll react with. A chemical equation is actually just a way of saying, it's basically a way of depicting, without writing it out in detail, in symbols and numbers, what's happening in the chemical reaction. In other words, give the chemical formulas of the chemicals that are reacting. Give the chemical formulas of the chemicals that result from the chemical reaction. And then it turns out we have to do some other work, and that is make sure we know how many molecules of each chemical react and how many molecules of each chemical do we produce to make sure we have the same number of each element's atoms on each side. So we call this a chemical equation. It's a way to represent the formulas, the identities of the chemicals that reacted and the chemicals that actually formed. And we'll get more familiar with this, the molar amounts of them. So in a chemical equation that's depicted here, we put some gas together. We put some methane gas with oxygen gas. We produce carbon dioxide gas and water gas. And there was a colored reaction that came out. Anyway, the chemicals that are on the left side of this arrow, the arrow means reacts, produces, forms, whatever you want to call it, are called reactants, simply because they react together. And then the compounds, the products, the chemicals that are on the right, the ones that are produced are products. So, awesome. Little side note, how do you know that a chemical reaction is happening? Basically, it depends upon can you see the difference between what the chemicals look like before and after. So a couple things that distinguish one chemical from another. Not all of them are nice and colored, but we might have a couple things. Number one, let's say we had two solids react, but the new substance you produce is a gas at the same temperature. You might get a gas for that new chemical. So changing phase. You got solids on the left, and now you got a gas. You got a liquid and a solid, you get a gas. You got two liquids, you produce a gas, whatever. So that's just saying I got a phase change. One of my new products is not the same phase as my reactants. So I'm surmising that I didn't boil anything. I just formed a new substance, which is a gas at the same temperature that my reactants were. Here's another one. We got two liquids that have chemicals in them, and they react together, and instead of making a liquid, you make a solid. A precipitate is called a solid. They call it precipitate because it's because of the context of it being formed with a liquid. Then you can also look for the energy. Sometimes energy is given up by reactions, and sometimes they cool down because they absorb energy. So heat or cold can actually signal a reaction happen. All right. So when you write these out, you have to make sure you have the right formulas. That's last chapter. Got to know the formulas, otherwise we can't balance the reactions. So the formulas must be correct. And the number and type of each type of atom must be the same on the reactant side. This is called law of conservation of matter. And that's what we're concerned with today. Make sure when we write out the reaction that we have the same number of each element's atoms on the left with the reactants and on the right. Now, you might say, well, what if the formulas don't agree? They won't. But you can always put in these numbers here and change the numbers of atoms by putting in what are called coefficients. So, big word, coefficients. You can change those, and you can put, when you first write it out, you're going to assume everything's a onesie. But if things don't add up, like over here, let's pretend this is a 1, and let's change this to 2 oxygens. We're going to count up our atoms. We have 1 carbon, 2 oxygens, and 4 hydrogens. Let's count on this side. We have 1 carbon, 3 oxygens. So I'm going to take away this one. I'll put a 1 here. And 4 hydrogens. 2 hydrogens, sorry. So we got a whole mess there. So we have to do something to make this work. So carbons are okay. But can we double our hydrogens on this side? We got 2 here, we got 4 here. So what we do, instead of just saying, I'm going to change that 2 to a 4, you're going to put a 2 in front of this guy. And when you do that, you know full well that you have a different problem. You got your H's balanced, but now you have 2, 4 oxygens. So if you have 4 oxygens, what about this guy? Change that to a 2. So that's the type of things we're going to do. We can't change O2. O2 is oxygen. It's 2 oxygen molecules, 2 oxygen atoms sharing electrons. CH4 is what it is. We can change the numbers of each molecule. So when we have it all said and done, 1 molecule of methane reacts with 2 molecules of O2 to produce a new 1 carbon dioxide molecule and 2 water molecules. That's how you can separate the number of atoms here and recombine them into atoms here. You have obeyed the law of conservation of mass. Next thing we're going to do is learn how to translate. So we're translating by actually putting in the symbols for our names of our chemicals. We know how to do that. But we're also going to put in some new translations. Very small ones though. So notice up here, solid. We have a symbol for that. Aqueous. We have a symbol for that. By the way, we got sodium. It's an element. It's just Na. Hydrochloric acid, we can put our formula for that. We know how to do that from last chapter. Here's another aqueous, and here's a chemical. Here's a chemical. So that's what we're going to translate into symbols and words, and then we're going to balance it. So here we go. Let's go to the next part here. Sodium. Translated. By the way, we put S because it did say solid. You remember that? It did say solid. Yep, it says solid. Next one said aqueous. So the two things that react according to the sentence were solid sodium, aqueous hydrochloric acid. Now, I'm going to talk about these elements in a minute, but assume they're onesies. In other words, you might say, well, of course they are. Well, you don't know that for sure. I mean, all you know is it's one type of atom, it's sodium. But for now, I'm going to say most of them are onesies. Hydrochloric acid. You didn't just write out HCl. You actually said H is +1, chlorine is -1, and you did the crossover. So you do know for sure it's H1Cl1. Then you said it made sodium chloride. Notice we put the aqueous for AQ here to say, by the way, aqueous, what is that? So we got solid is S, liquid is L, gas is G. Aqueous means it's dissolved in water. Aqueous. So aqueous is AQ. We made it sodium chloride, but how we got that is we put in our charges, we crossed them over, we did our due diligence, making sure we got the right formula and the right subscripts. It just so happens they're onesies. Interestingly, hydrogen gas is H2. So anyway, that's our skeleton equation, by the way. Now I want to say something about the fact that you might say, well, how did you know it was H2 and why is it H2? How did you know it was Na? Let's do some elements real quick. Here it is. So for all elements, I want you to assume that they're onesies, except for these guys right here. There are 7 diatomic elements. What does that mean? When you put them down, it says nitrogen gas. It's in the 7. It's in the shaded part that's a 7. You put N2 instead of N1. If you see fluorine gas, it's F2. If you see bromine gas, it's Br2. If you see iodine, solid iodine, it's I2. By the way, there's also a hydrogen up here, H2. Those are the 7 diatomic elements you need to memorize. Now, what you do, you don't really memorize them. You just look at the periodic table and say halogens and go left 2. You say, yeah, nitrogen gas, heard of it. Now you remember it's N2, O2. Go down 4 halogens, then add your hydrogen. So you really don't have to memorize them. You just have to know where they are in the periodic table. So let me see here. So now I explain. So everybody else is a monatomic. So I got the right formulas. That's step 1. Write formulas and put the phases if they're given in the sentence. So this is called the formula equation because we haven't balanced the atoms yet. So let me see here. Okay, I talked about the monatomic elements. Let's go to the next thing. Phases. Here are some symbols we need to know. Not all of them, though. First of all, I would rather you put a double arrow to reflect the fact that all reactions are theoretically reversible to some extent or another. That's the way to separate your reactants and products. You got your solid. Don't have to memorize this, but we might see it later. That's when you put things together that are not solids at all, and all of a sudden you get a solid, especially if you put 2 liquids together. But precipitate, by the way, is a solid. They call it precipitate because you have 2 liquids mixed together. All of a sudden, out of nowhere, a solid comes, a new chemical, and it falls to the bottom. That's why I call it a precipitate. Liquid, dissolved in water, gas. Here's another alternative to gas. A lot of times that's a surprise too. You put a liquid with a solid or 2 solids together, or a liquid and a liquid, and gas comes off. Remember, when gas comes off, it floats up. So this is a way to get their attention to say, this is a gas. All the rest of these things are to basically say this. When you have the arrow or double arrows going from reactants to products, these are all the different things you can write above them and say, this is what you have to do to make the reaction work. You got to add heat. You got to do it at this pressure. You got to do it at this temperature. You got to add this catalyst. Just to say, you can put other information above the arrow to tell you how to do the reaction. So basically solid, liquid, gas, aqueous, and that's about it. Okay, let's balance it. Now, what we do in the balancing, let me take a quick, so I'm going to discard it. I'm going to go to inserting a slide. There we go. Okay, so let me write out the reaction we just had. I have to remember what it is first. Slideshow and from coincide. Na plus HCl. Okay, Na plus HCl. Na solid plus HCl aqueous. Am I in the right slide? Hope so. Then we got the arrow, and we got basically NaCl plus H2. Okay, anyway, we're going to balance this one. So now, when you write that out and you write it, you might already trying to be adding it up or balancing it. Don't do that. When you're doing the formulas, it shouldn't add up. Sometimes it does, by chance. But don't make it add up. So don't say to yourself, nope, that can't be H2 because I only have one H over here. Don't do that. Be blind, be dumb, and don't add them up. You're not supposed to do that. You can add them, you can make the atoms add up later because these formulas are written in stone, etched in stone from God. These are the formulas for these compounds, whether they add up or not. You're going to make them add up by doing this. Now, tips for balancing chemical equations. I always do H's and O's last, and if you have both hydrogens and oxygens, H's and O's, do the oxygens last because they always end up being kind of hard. I'll show you why in a minute it matters. So I'm going to write out the 3 types of elements I see on both sides. Sodium, chlorine, and hydrogen. I'm going to count how many are on each side. So 1, but on the product side I have 1. Chlorine I have 1. I have 1 chlorine on the other side. H I have 1, and here's our problem. I have 2. So what you can do with this, you don't change the subscripts. You put numbers to multiply the one that has the lowest. So what I mean by that, the HCl has 1 H. Let's make it 2. I can't put a 2 here, though. It's against the rules. But I can put a 2 here. Now, the problem with that, as you might know, is that you're going to cause a different problem. But you're going to eventually get it to work. So what's the problem? You got 2 H's, but now you have 2 chlorines. So you screwed up something. Okay, go with it and say, I'll fix what I caused. You might feel like you're chasing your tail, but just go with it. So I'll put a 2 there to get my chlorines right, but now I have 2 sodiums. And finally, you put a 2 by the sodium here, and you're like, oh my goodness, everything's done. I'm done. It worked. Oh my goodness. Cool. So anyway, that's how you balance. So the next couple slides show me kind of explaining that, but the best way to explain it is to actually do it in front of you. Whoops. Okay, let's try another one. Yeah, sodium oxide. Reason I wanted to do another one is on the quiz, and also just to make sure you're really competent at saying, I gotta get the right formulas. So sodium oxide. Now sodium oxide is NaO. Your mind should click and say, I need to put in the charges since it's ionic. So sodium oxide is not NaO, it's Na2O. It reacts, it's added to water, and then you form sodium hydroxide. The sodium hydroxide, Na. Now on the quiz and stuff, you can use your polyatomic sheet and your charge sheet. Not the first 2 pages of the cheat sheet though. Hydroxide is OH with a -1, +1. So this is our correct formulas. I made sure I did all the crossovers and stuff. Because if they're not correct, you're not going to be able to balance it. Then if you do what we just did, the whole rigmarole, by the way, I'm going to do Na, I'm going to do H and O last. Always do O last and H second to last if there's an O, or do H last if there's no O. So I got 2 sodiums, careful, 2 oxygens, it's in 2 places, 2 hydrogens, and over here I see 1 of everything, 1, 1, 1. So all I need to do is put a 2 there and I'm all set. Cool. Again, the biggest thing to do with this is to do as many as we can together. Okay, here's another one. Oh, we're not going to do sentences. But we did these in class. Some of these are not that easy to do as far as balancing. So I didn't give you the phase for C6H12O6. I gave you the formula because we don't know the names of biochemicals. But we do know that oxygen gas is O2. Remember, it's a diatomic element. It does say gas, so I'll put that in. It produces, arrow, carbon dioxide, CO2 is the right formula. And water is something everybody knows off the top of their head. Now we're going to count. And remember what I said. Always put H no last. I call it whole. So we're going to count our carbons. We have 6 on this side. Only 1 on this side. 12 hydrogens versus 2 on this side. And our oxygens, be very careful. They're in 2 places in both sides. 8. And we got 2, 3. That's a horrible ratio. So that's why we do the oxygens last, is we're hoping to change the oxygens as we change the carbons and hydrogens. So what do we do with the carbons? Let's add a 6. So what happened to our oxygens? 12, 13. Let's fix it. We don't want to deal with the 8 versus 13. Let's try to fix our hydrogens. Let's put a 6 in front of the H2. We didn't change the carbons, but our oxygens now are 12 plus 6 equals 18. And you might say, well, wait a minute. No. You might say, well, okay, I can multiply it by 8 18s or whatever. You can only use whole numbers. And by the way, we have 2 choices. We can put a number here to get our oxygens up from 8 to 18 and here. So you might say, first of all, I can't, if all the oxygens were in one place, I don't have a whole number I can multiply 8 by and make it 18. But it's actually a little bit different. I'm going to say, after you think about this riddle, how to get your oxygens on the left to 18, that you do not want to fiddle with this 6 over here. So if you put a number here, you're going to screw up the carbons and hydrogens. Then you'll have to go back and change these, which will change the oxygens. You're going to be chasing your tail then. I'm going to argue that you only want to change this one. So if you change this one, notice that you're going to go 2 times whatever coefficient you choose. You're going to have a 6 to always add to it. And that will equal your 18 that you're not going to change on the other side. So you really have 2x equals 12, x equals 6. If you put a 6 there, you're going to have it. Here's one, lithium, 1. That is oxygen gas is actually diatomic. lithium oxide, +1, oxygens -2, Li2O. Yes, this one is very easy to say it's LiO2 because you're like, I need to balance it. No, you don't balance it when you're putting in formulas. It's not supposed to necessarily balance by putting in the formulas. It's okay to be off. Everyone we did so far is off. So we'll put lithium, and we always do oxygen second or last. Got 1 versus 2 and 2 versus 1. So let's pick lithium. Let's put a 2 here. We're like, that's nice. Now we have to do something with the oxygen on the other side. So if we put a 2 here, you're like, oh, that's just great. I just screwed up my lithium again. I'm up to 4 lithium. Well, go back and change this 2 to a 4 and you're all set. Let's try another one here. Whoops, didn't mean to do that. Chlorine gas. Whoops. I guess I have to go all the way back. Remember, chlorine is diatomic. It's in the 7. Iron, though, is actually monatomic. And I didn't put the state of it. Iron 2 chloride is iron +2, chlorine -1. So I got this. Now this one freaks out people because they're like, is it supposed to be balanced already? It can be, and it is. You're done. Okay, so anyway, that's pretty good for practice. Now, the last thing I actually did is there's harder ones to just balance. So we're going to go to the mode of just balancing equations. Let's go back up here. And I'm going to show you a couple tricks. Number 1, that we listed as far as things to remember. And we saw this with the glucose plus oxygen equals carbon dioxide and water. H's and O's balance last when you see them. If they're busy, they can be in multiple spots. If there's both H's and O's, hydrogens and oxygens, H and then O. The last 2 will be H and then O will be the very last. Number 2, I need to show you what to do with polyatomics. Instead of writing it down, I need to just show it so then you can describe it the way you want to do it. So here we go. Okay, you're like, what the heck am I going to do with that? You had oxygens in 2 places on both sides of the equation. But do you notice that the CO3 stays as a CO3 and the PO4 stays as a PO4? I want you to simplify this by counting how many CO3s you have. Don't separate it out into carbons and oxygens. Leave them as is. So when you do this one, I want you to list out lithiums, CO3s as a unit, barium as an element, and PO4s. Polyatomic atoms treat as like a single element. So now count up, I have 2 lithiums versus 3, which is scary. 1 carbonate versus 1 carbonate. 3 bariums versus 1. And PO4, I got 1 versus 1. Yeah, that's right. Oh, I made a mistake though. That should be a 2 there. 2 versus 1. Okay. So let me make sure I got that right. Okay, good. So, number 1, if you do see a 2 versus 3, don't do anything with it until you try some other stuff and solve other problems. When you solve those other problems, the lithiums are probably going to change, and then there'll be multiples of each other. So what's wrong with the 2 versus 3? Are you going to make 2 equal to 3? You can't multiply it by 3/2. Why? Because they're not allowed to put in fractions. So right now, there is a way to deal with 2 versus 3. That'll be my next trick. You could try to multiply this side by 3 and this side by 2. But you don't know you need to do that unless this is the last thing you have left. So let's not do it. So let's go to the barium first and do everything but the 2 versus 3. So let's put a 3 here to get my barium up. And now all of a sudden I have 3 carbonates. So you're like, wow, it looks worse than it did before. Solved one problem, created another. Okay, pick your poison. I'm going to go back to my carbonate and try to get that up to 3. So I'm going to put 3 in front of here. But now I have 6 lithiums. Oh, that's actually good. Well, do you want to try your lithium now and double it, or your PO4, either one? Well, what do I have to do? I have to go to the right side, which has less. So I need to put a 2. But turns out I solved both problems with one swoop. There's a 6 and there's a 2. So my lesson in this one was twofold. Number 1, did you see that I didn't separate into carbons and oxygens? You'll never get it balanced. Keep them together. Count how many carbonates, how many phosphates. Number 2, I had a 2 versus 3. I avoided it, and it rectifies itself. So let me try another thing. We're almost done. I'm going to try another equation. Li3PO4 plus magnesium. And then I get magnesium 3PO4. I'm going to put parentheses around this. PO42 plus Li. Okay, well, no, let me think about this for a second. Trying to create a situation where I have a 3 versus 2 and I have failed. Let me try a different, let me see. Let me try another one here. I'll figure this out someday. Okay. Oops. Okay. What I'm going to tell you is this. I'm trying to figure out how I came up with a 2 versus 3 scenario. If you do get a 2 versus 3 scenario, let me just talk you through this. What you have to do with the side that has 2 of the thing is multiply by 3, and the side that has 3 of the thing multiply by 2, which means you're going to try to get both of them to 6. And then I guarantee you, if everything's okay, all the problems you created by multiplying by 2 on one side and 3 on the other side, you should be able to rectify, actually. So let me see if I can figure one out. I'm starting to remember how to do this, how to come up with a problem. So this is a 2. Shoot. I am trying here. Okay, now I remember how to do this. Sorry. Aluminum nitrate plus magnesium produces magnesium nitrate plus aluminum. You say, okay, what's going on with this one? What's the big deal with it? So we got aluminums to count, NO3s to count, get magnesiums to count. So 1 on each side for aluminum. NO3 is a 3 and a 2. Magnesium's a 1 and a 1. There you go. We got 3 versus 2 and you can't avoid it. Everything else is balanced except for the 3 versus 2. So let's try to make yourself feel good that you can watch this be done. Times this side by 2. Times this side with NO3 by 3. Let's see if we can rectify this. So this 2 gives us 2 aluminums. This 3 over here gives us 3 magnesiums. Can we correct our damage after getting our 2 versus 3 correct? Yes, we can. Put a 2 in right here and put a 3 in right here. You're all set. So if you have to do a 2 versus 3 because everything else is done, go ahead and shoot for 6. That's called the least common multiple method. And then you should be able to correct everything all the damage you caused. So that is it for today. Be able to balance chemical equations. Be able to translate them. Remember the little tricks. Not all of them are straightforward. Watch out. Remember our tips are keep your polyatomics as a unit. Don't split them up into atoms. O's are always last. H's are always last or second to last if there's an O. The 2 against 2 versus 3 thing we have a strategy for. If you have a 2 versus 3 and you have other things to work on, that are not balanced, don't do the 2 versus 3. Do something else first. And those things will get you pretty far. So that is it for today.